Hello everyone, and welcome back to another Engineering Statics lecture video. I hope you guys are all doing well and are ready to learn, so let's get started. So in 2D, it's very easy to determine angles vectors make because it's 2D. It's very easy to visualize, draw it out, and use some trigonometry to find these angles. However, in 3D, well, it kind of sucks. It's three-dimensional space. It's not exactly easy to draw. It's not easy to analyze. So what do we do in 3D? Well, we actually use something called the dot product, all right? So dot product, dot product, dot product. I want you guys to associate angles with dot product, okay? If you ever see an angle question, dot product. Hopefully I got that stuck in your head. Maybe a little bit annoying, and I apologize, but I really want you guys to remember that. Now you guys may be saying, Clayton, what is the dot product? Well, it's actually a very nice simple formula where we take a vector A and we dot it with a vector B. Now, this gives us the magnitude of A multiplied by the magnitude of B times cosine theta. Now, you guys may be saying, Clayton, what's so special? Well, if we look at the very right side of this formula, we have a theta there. And that theta is actually going to be the angle between vector A and vector B. So using this formula, we can actually find the angle between two vectors. So if we have two vectors here, A and B, and I wanted to find the angle between them, which is that theta, I'm going to use the dot product. And you guys are saying, all right, Clayton, that's easy. If I look at the right-hand side, we have the magnitude of A. I know how to find magnitudes. Magnitude of B, piece of cake. Cosine of theta, well, I have a calculator, so I can figure out what that is. Oh, wait a second. What about that left-hand side? So this is where it starts to get a little bit tricky, is how do we calculate that A dot B? Well, it's actually really simple. Looks bad, very simple. That's actually most of engineering if you think about it. Looks really bad, it's actually pretty simple. So A dot B, if I define two vectors, A and B, A dot B is actually just going to be each component multiplied by each other added together. That's it. Now, you guys are saying, Clayton, whoa, you're talking a little bit too fast there. What exactly did you say? Well, all we're going to do is we're going to take the two x components, multiply them together. We're going to take the two y components, multiply them together, and the two z components, multiply them together, and then finally we're going to add everything together. We're going to sum it up, basically. If we're adding everything together, if we have all of our components as three separate piles, and we clump them all together and add them together, we are going to get a single number, all right? A single number, because we're adding it all together. This means that A dot B actually produces a scalar. It does not produce a vector. It produces a scalar. And if you look at the title of this slide, I kind of hint to that because another name for the dot product is actually called the scalar product. Okay, so if you guys do a dot product and you somehow get a vector, you guys did something wrong, all right? It should produce a scalar, and the formula, as we can see, it's not too bad. Now, here's the first trick when it comes to dot product, and I find that a lot of the professors forget to mention this, and it creates a lot of confusion with students. We can dot any two vectors together. If A was a force vector and B was a position vector, no problem, we can do that. If A was a unit vector and B was a force vector, again, no problem, we can do that. You guys don't have to worry about making sure that the two vectors are the exact same. We're going to talk more about why that is in the next slide. Now, the last little trick here is that it's associated. Distributive. I always forget those words, and we're going to talk about them more in the next slide. But basically, A dot B, it's going to be the exact same as B dot A. So you don't have to worry about trying to get order right. And this is very simple. If we look at the formula, we're multiplying the two x components together. It doesn't matter if we go 2 times 3 or 3 times 2. At the end, it's going to be the exact same thing. All right, so when we look at the dot product, some of you guys may be saying, Clayton, I don't know, it seems pretty sketch. You seem pretty sketch. How about a proof? Well, no problem at all. Now, the dot product actually has a lot of different proofs, but I'm going to show you guys perhaps one that you guys find the most easy. And that is this. If I want to go A dot B, I'm going to essentially write out all of A, and I'm going to write out all of B, and we're going to start multiplying everything together. Now, the thing to keep in mind here when we're actually looking at this, and this is something we don't really talk about because you don't need to know, but I, J, and K, they're actually vectors. And they're, more specifically, they are the vectors of the three-axis systems. So for example, I would be 1, 0, 0. J, which is the y-axis, would be 0, 1, 0. And K would be 0, 0, 1. Again, not something you really need to know, but for this proof, if you guys know that, it'll make a lot more sense. So let's say we multiply everything together, we end up getting something like this. You guys are saying, Clayton, you're supposed to prove it, not make it worse. I'm sorry, but don't worry, this simplifies very nicely. Because remember, for the dot product, we had the following formula, where a dot b, or two vectors dotted together, is equal to the magnitude of the two vectors multiplied by each other, and then multiplied by cosine theta. Now, remember what I said, I, j, and k are actually the three axes. So if we were to consider two vectors that are the exact same and dotted with each other, well, we know that's actually going to be equal to 1 because the angle between them is 0. If I were to take the y-axis going up and try and find the angle with the y-axis, well, they're the exact same. So, of course, the angle between them is going to be 0. Cosine of 0 is equal to 1. Therefore, anything where we got I dot I, or J dot J, or K dot K, we know it's going to be equal to 1. So we can take out those three components right off the bat. Now the next thing is if we dot two axes that are not the same, so let's say I take the x-axis and I dot it with the y-axis, well, we know the angles between them are always going to be 90 degrees. So in this particular case, if we have I dot J, J dot K, or I dot K, we know it's always going to equal 0 because it's 90 degrees. Cosine of 90 is equal to 0. As we can see, we're actually only left with three components. That is ax bx, ay by, and az bz. So therefore, a dot b is actually equal to ax plus bx, or sorry, ax times bx plus ay times by plus az times bz. Again, nice and simple. Now, the dot product has three properties, and the first one is commutative, which means that a dot b is equal to b dot a. Again, that's the one I mentioned on the previous slide. I got the name wrong, of course, but this is going to be kind of the nice one to remember because a lot of students start freaking out about order. Remember, in position vectors, it's very important if you go from B to A or A to B, they give you a different answer. Dot product, you don't have to worry about that. So A dot B is equal to B dot A, nice and good. The second one is associative. So if I were to take a scalar C and multiply it by A dot B, well, that's the same as multiplying A by C and then dotting with B, etc., etc. And the final one is distributive. I don't know why. I can't say these three words. I always struggle mightily. So if this is the case, if we have B plus C and then dot it with A, well, that's the same as going A dot B plus A dot C. All right, so again, the only real one that I would recommend remembering is that the order doesn't matter. You can go A dot B or B dot A. You guys will be fine either way. So yep, that's it for this video. I want to thank you guys so much for listening. I really appreciate it. I hope you guys have a wonderful day, and I will see you in the next video.